Yes, you had a question. Which one? The estimate? Primes in? Prime density estimate. Okay. Lemma 2, yeah. What is the doubt? That proof you have to finish. This is only the idea. Basically, you have to show that these prime powers p raised to v, they are coming only from the bigger numbers, upper half, not from the lower half. Well, on the spot, I cannot. You want the whole, all the details, right? Basically, any power that divides x, where x is in the lower half, 1 to n. So we have the lower half 1 to n, we have the upper half n plus 1 to 2n. Anything that divides lower half number x will also divide something in the numerator, so they will get cancelled. Yeah, but you can show that if for x and x prime, the powers get cancelled with y and phi prime. So the powers which divide 2n choose n, they have to come from something in the numerator, but that again is still not enough, because it's possible that what you are saying is happening for y and y prime. Part of p power comes from y and other part comes from phi prime. Then it could have been much bigger than 2n. Right? In lemma 2, you want to show that p raised to v is at most 2n. So if you have take a factor of y and take a factor of y prime and multiply it, then it will become bigger than 2n. So you have to show that that is not happening. Intuitively, what it means is in this part, so you want to show that p raised to v divides y, if p raised to v divides 2n choose n. So why can't some part come from y and another part from y prime, and the product is p raised to v? That is what you have to rule out. So that is being ruled out by saying that p raised to v has to be bigger than n. Actually, yeah, so that part is still hazy. You have to complete this. Let me move on with the topics. Let's not discuss these details here. So in groups, do you have any questions? There was a question in that proof of irreducible polynomials mod p. So that I have changed. You can read this in the notes. It's uploaded. Any other questions in finite fields or groups? Can we continue with groups? So in group, we'll have only one operation. Example is the symmetry group of symmetry on n elements. So that's Sn. So we say that a set G is a group if there is an operator star satisfying closure, associativity, identity, and inverse. Identity we'll call it now by E, because depending on the situation, E can be anything. So now it will be an abstract identity. And accordingly, there is an inverse for every element. Right? This has to be true for all A in the group, in the set G. Then you call the set a group. Um, Now there are some very special groups which we use all the time, which is called an abelian group. So maybe right here you can see that this group Sn, A star B may not be equal to B star A, right? Is this true? So depending on how, in what order you do the permutation, if you first do B and then A, or you do A and then B, the results will be different. But there are other groups, more basic groups, where this is true. So for example, what's an example? Yeah, the classical motivating case is integers with addition, and that is a group, is an infinite group. And here there is this property. So I write star here, but the star is essentially plus, right? That's the, maybe I should mention that operation only. So clearly, how you add, the answer will not change in integers. So this is, we'll give this a name, we'll call it a commutative or abelian group. If G is a group, and for all AB in the group, in the set, A star B is B star A. So this comes with the operation star. Okay, so if the multiplication, the order will not matter. So we had shown that parenthesis will not be important. Now we are saying that order also will not be important. Then you call the group an abelian group. So this example is clear. The other example is that of matrices, right? N cross n matrices with plus. Is it a group? So n cross n matrices, or it can also be m cross n. They don't have to be square matrices. So m cross n matrices with addition, you have all the properties, right? So this is an abelian group. What about square matrices with multiplication? Is this a group? Does every element have a multiplicative inverse, giving the identity matrix? Right, so this is actually not even a group. But you can take what is called GLN-F. So this is the invertible matrices only. So general linear group. This is the general linear group. Okay, so if you only look at multiplicative inverse, so only the matrices which are invertible, then that set will form a group, because when you multiply two invertible matrices, you always get an invertible matrix, right? So that will form a group with identity, E being the identity matrix. Is this abelian? So you have learned that A times B, if A and B are matrices, may be different from B times A, right? Um, are they the same for 2 by 2 matrices, AB equal to BA? So even for n equal to 2, this is not an abelian group. It's only for n equal to 1 that it is abelian. So this is non-abelian. For n greater than 1. Okay, so for all 2 by 2 and bigger matrices, you have the general linear group GLN is a non-abelian group. Okay. Okay, one simple property you should prove from the axiom is that the E in a group is unique. Can you prove this? Just from the axiom of a group, the identity element is unique. So suppose E1, E2 are identities in G star. How do you show that E1 is equal to E2? Yeah, so the key operation here will be just multiply them. So because E2 is an identity, this will be E2 or this will be E1, and because E1 is an identity, this will be E2. Right, so that's it. So it shows that identity element, there cannot be two identity elements. So now you can read the axiom as there is a unique identity element E. And for the inverse, similar proof you can give. Let's do that just for exercise, just to warm up. So suppose A star A1 and A1 star A is identity, but it's also A star A2, A2 star A. We want to show that A1 is A2. How do you show this? Just by group axioms. Any ideas? Yeah, so the very first expression you can multiply on the, so there are two sides of an element, right? So one, the right side is occupied by A1, left is free, so you multiply that by A2. So if you do that, then A2 A1 is A2 star E, which is A2, and yeah, and I can also, so here I use this, but I could as well use this. And so A1 and A2 is what we call A inverse. Okay, so inverse is unique. So when I say A inverse, just by the group axiom, it's a unique element. It's a function which is basically a permutation of the group. Okay, so if you look at inverse, then elements A1 to AN will be permuted to something else. It's unique. Okay. Yeah, so just let us look at more examples. We have seen matrices, integers, and permutation. So other examples are, you can take well, integers with plus, we have seen. You can take rationals with plus. You can take complex real with plus, complex with plus. These are obviously, all of them are groups. They are abelian groups. And the identity element is, yeah, the identity element here is 0. Yeah, not 1. That's important. What about if I remove 0 and then do multiplication? So this will not work, right? This will not give you a group, because 1 and plus, so minus 1 plus 1 will be fine, but if you look at 2 or minus 2, you will not get an inverse. So under multiplication there is no inverse, but with Q star, what do you get? You get an abelian group. So abelian, and E here is, what is the identity element? Yeah, now this is with identity element different, which is 1. And okay, something more interesting you can do with rationals, which is take only positive ones. So what do you get? So positive rationals or reals will again form a group, right? Because every positive, there is an inverse. The reciprocal is again positive. And the identity element is the same. Right? So this is a strictly smaller, so it's a subgroup of Q star R star. Okay, what else? Yeah, and then we can move to discrete math, which is, you have Z slash N. So with plus, you get what? That's an abelian group. And identity element is the representative 0, right? What do you get with, so with multiplication, is this a group? Zn comma star? No, yeah, so okay, let's write that down. Then you are wrong. Is this a group? Yeah, this is not a group. So we have to do star. I mean, we have to remove 0, and then under multiplication, it's abelian and identity changes. It's the 1. And same thing you can do with any Z mod n, right? Z slash n, comma star, if I want to see it as a group, I should do what? I should do a star, where now this is not just removing 0, this is actually the co-prime numbers, right? So I seem to be overusing star here in the superscript, but I hope you can understand what's going on from the context. So Zn star, which is the co-prime numbers. of size phi n. Okay, so these elements under multiplication, there is inverse. It's basically rehashing the Euclid GCD algorithm. And the identity element is just 1. Okay. Any questions? So you have seen a lot of groups now, abelian, non-abelian, and also non-groups. Generally groups, complicated groups come from transformations. So which is this symmetry transformation, permutations you saw. In permutations, you can also throw in one more symmetry transformation, which is reflection. That will give you a new group. So for example, you have, let's say you have a polygon. So this labeling that I have done, it is arbitrary, 1, 2, 3, 4, 5, 6. So I can actually permute it without changing the picture. Okay, so the embedding of the hexagon should not change. Labeling is allowed to be changed. So how many transformations are there? Just 6. Yeah, I mean you can rotate, that is 6, but you can also do something across this line. You can flip, right? So you can send 1 to 5 and 2 to 4. I mean you can swap 1 and 5, 2 and 4. Don't change 3, 6. If you want, you can also swap 3, 6. So these transformations are also there. These are not the cyclic permutations, right? So simple things are you can send 1 to 2, 2 to 3, 3 to 4, 5 to 6, 6 to 1. That will not change the picture, it will only change the labels. So those are the rotations, and then you have reflections. So symmetries of a regular, which means sides are equal, of a regular polygon, whereby symmetries we mean that the picture should not change, only the labels are allowed to change. So I mean clearly 6 factorial is the maximum you can do, but not all of them are good, right? Some permutations will change the picture. So symmetries of a regular polygon under composition. So these examples are the rotation or reflection. And their compositions, right? So this again will be a group under composition of permutation. It will be a group, and it will be smaller than S6. It will have the identity element the same. This is called the dihedral group. Okay, so this will be for n-gon, it will be dn. So this D6 or Dn will be subgroup of Sn. Is that clear? Yeah, if this symmetry is not clear to you, just remember that when you map 1 to 6 to a permutation, what you want is that the edges should not, I mean the edge connections should be preserved, should be respected. Okay, so there is an edge between 1 and 2. So wherever you map 1 and 2 or move 1 and 2, there should be an edge between 1 and 2. And there is no edge between 1 and 3. So wherever you map 1 and 3, there should be no edge between 1 and 3. Okay, so you are not allowed to just arbitrarily relabel. That will be just S6. You have to respect the edges between ij. Then you get Dn. Is that clear? That's the dihedral group. Yes. Sorry, what is D6? So 6 rotations and lots of reflections, but I don't know what is the size. Sorry? Yeah, so that's the exercise. I don't want to commit to anything that you can use against me. So okay, D6 you show is 6 times 2. Okay. So obviously you saw a pattern here when we constructed these examples of groups. We used a field a lot, right? So in general, obviously you can play this game. So if F is a field, then what is F plus? F plus is an abelian group. And what is F star star? Where by F star I mean remove the 0 and then look at the multiplication structure. That's also an abelian group. Okay. So if we had started with the definition of group, then we could have defined field in a shorter way. You could have just said that there are two operations in a field. With plus, it's an abelian group, and with multiplication, it will become an abelian group if you remove 0. And star will distribute on plus. Okay, and so just with these 3 axioms, you will have a field. Okay, so field is a special case of a very special case of group because this multiplication here is also abelian. Instead of this, if you look at the matrices, then in addition it's an abelian group. In multiplication, it's neither abelian nor group. Okay, so a group is completely defined or completely specified by its what is called multiplication table. You just have to tell the rules of multiplication, right? So this is just, it will be a table where you have columns are A1, A2 and rows are indexed by A1, A2. And then in AI, AJ you have to say basically you have to say that what the product is. Okay, so it's just this matrix. It may be finite matrix or an infinite one. We call it a table. So it is finite if the group is finite, otherwise it is infinite. And you just specify what is the result AJ times AI. This completely specifies the group, right? But is this table, is this matrix an arbitrary one? I mean, are the entries correlated somehow or are they completely different? So for example, when you see any row of this table, what is the property of the row? Do you see all the elements? Or can some element of group G be missing? So let's write some properties of this table. Every row, respectively column, has distinct elements. Okay, no element repeats, which means that you essentially have a permutation of A1 to AN in every row and respectively in every column. Why is that? Sorry? Right. This is the inverse axiom. So, so jth row is AJ times A1, A2 dot dot. Right, and if two elements are equal, then it would mean that AJ AI is equal to AJ AI prime, but then AJ has an inverse, so which will mean that AI and AI prime are same. Okay, so every row is a permutation, every column is a permutation. So it's kind of a magic square, special matrix. Okay. Yeah, maybe you can see it in this example. So if you take G to be Z4 star star, Z5 star star, right, which is the same as the field structure basically. So the elements are 1, 2, 3, 4. 0 is missing. So you will have 1, 2, and then you do what? You do star, right? So here you get the same, and here you get 2, 4. What is 2 times 3? That's 1. right? So you can see that rows distinct elements and columns also distinct elements. That's the multiplication table for this group. So now we study an important property in groups, which we have alluded to before, which is order of an element. So yeah, so for an element X, in a group, order of X is the least number I such that, what do you want? You have seen a similar definition in the case of fields, right? Multiplicative order. So now here we simply call it order because group has only one operation. So with respect to that, the order is the least number such that with respect to star, if you do it j times, then you get E, right? So x to the j just means that the operation is star and you repeat it j times. X square is basically x times x. X0 is by definition E. X1 is just x. Okay. So the least number which yeah, okay, and order of E we'll just define it to be something by convention. Maybe we define it 0. Not well. In that case, it will not exist. I mean, positive. Maybe I should say G minus E here. And for order of E, I can define it to be 0. That should work. Oh no, it will not work actually. You should define it 1. Well, then I don't need to define it. Then the previous thing was fine. Okay. Yeah, so for order of E is implied to be 1, and there is no other element which has order 1, right? Okay, that's fine then. Yeah, so the identity element E has order 1 and every other element will have order 2 or more. That's the right definition. Another thing you can show is that order of X inverse is the same as order of X. Right? For any element X, you can see that x to the j is E if and only if x to the minus j is E. Where, okay, what is minus j? This is defined to be X inverse and then multiply j times. Okay, that would be the definition. For all j integers and for all x in the group. Okay, so we are allowed to exponentiate by positive, negative and 0 numbers. All integers are allowed. With negative, the interpretation is that you are first doing inverse and then you are multiplying j times. Okay, that will be the notation in abstract groups also. Yeah, so prove these properties. if you don't immediately see the proof, this will just help you warm up with the group axioms. And okay, there is one more thing here. So what do you think will happen if I do the opposite thing, which is I first multiply j times and then take the inverse? What will I get then? Sorry? Yeah, then also you will get the same thing. Okay, so this x to the minus j is quite flexible. You can either do x inverse first and then multiply j times, or you can multiply j times then take inverse, or you can do a combination of this. Everything gives the same answer. Okay, so which is why x to the minus j is the correct notation. It doesn't matter how you compute this thing. It's always the same answer. Okay, so now comes a strong property. It is strong because this group is defined in an abstract way. We will actually characterize what this number order of x is. Okay, this number cannot be arbitrary. These are special numbers. So, well, first of all, why should it even exist? Sorry? This number may not exist, right? Order of x may not be anything. Because I am asking for a natural number j, maybe there is no such number. It doesn't follow from the axiom. Yeah, so let's show that. If G, the size of the set G is finite, G is a finite group, then for all x, order of x exists. In fact, it's, you know that it will be in this range. How do you show this? X raised to G will be 1, will be E. How do we show that? Mm-hmm. Yeah, so that is an excellent suggestion. Let's show this to the other students. I don't want to give it the whole space for a particular reason. So what is being suggested is you look at this product. So your group is, let's say, G1, G2, Gn. Element is x, so you look at these elements x G1, x G2, x Gn, right, and then you take the product. What is this product? Can you simplify this? What is it? X to the n times pi of g. So do you believe this arithmetic? Why not? I mean, is this arithmetic true for matrices? So this is bogus, right? You can't do this. So this is only true for abelian groups. Sorry? No, no, are we still in this or are we changing the proof? No, no, we will change the proof, don't worry. But let's continue with this bogus line of argument. So for an abelian group, what this will imply is that x to the n there is one more step, right? So this thing is, xg is simply a permutation. So in the product, this is the same as product of g for all g. So which means that you have deduced x to the n is 1, is E. Okay, so for an abelian group G, this is the proof that actually you saw in Fermat's little theorem and then Euler's theorem also. Okay, that proof actually comes from here. This is the more abstract proof. This proof obviously doesn't need G1 to Gn to be numbers or anything. This is just symbols satisfying group axiom. Okay, so that's the idea. This tells you that x to the n, which is size of the group, this is always the identity element. Okay, but the problem is that this assumes abelian axiom, which is true for numbers. So if FLT and Euler's theorem holds fine, the proof is the same. But for matrix algebras and more complicated thing, it will not be true. Right, so with that detour, what do we do with non-abelian groups? Yeah, so we do this nice trick, which is you look at the group which is generated by a single element, that is x. So yeah, let's just call that cyclic group. Okay, so cyclic group generated by x, I will denote it by parenthesized x. It has essentially elements powers of x. Well, okay. I don't need all the integers, maybe just natural numbers. Okay, so you just keep powering x. Your group is finite, right? So you will only have finitely many elements. So what can you say about this set? First of all, is this a group? Because I'm calling it the cyclic group, so it better be a group. Why is that? Actually, let me make that proof trivial by putting z here. Okay, then it is clearly a group because there for x to the j there is x to the minus j. Okay, but in this there is also e because we have x to the 0. Right, so this is a cyclic group generated by x. But this happens to be by definition a group. How do I use this to prove the claim, to compute the order? Yes, so that is true. So now you do basically pigeonhole on this set. Okay, since I mean, by definition, it's an infinite set, but then since everything here lives in the group G, in the set G, which is a finite set, so clearly two elements here have to be equal. So X has two elements equal. Okay, which means that x to the j and x to the j prime for different jj prime, they are the same, which means what? Their difference is giving you 1, right? But the difference is not 0. This is some number. You can assume it to be positive. So you have found x to a positive number which is giving you 1, which means that there has to be an order. Okay, so this shows that there is an order. Moreover, you can show that the order cannot exceed G, the size of G, because it's the same argument. Yes? Wait, what? No, x is an element in the input. I am not talking about x exists. For all x in G, right? So you given an x in the input, this argument runs. X isn't a special element, it's any element. Is that clear? Yeah, so the orange part is a misguided proof, but works for number theory. But in general algebra, you have to be more complicated. Okay, so you have to give this abstract proof. But then you learn about these elements x to the j, which will turn out to be very useful. Okay. No questions? Sorry? Are new? What do you mean? Why did we define it? No, we just wanted to look at the set x to the j's. It happens to be a group, which I will call cyclic group. I mean, that object is the underlying principle in this proof, that you are looking at all the x to the j's. But yeah, if you are saying that we don't need the group structure, it's also fine. You can just look at the set of x to the j's, and there two things have to be equal. So order cannot be g plus 1 or more, because if it was g plus 1 or more meaning including infinity, then this set x to the j will have two equal elements, and there will be a contradiction. Okay. So, yeah, so as I promised before, this we will actually show that orders are very special numbers. They actually, not every number between 1 and size of the group G is of interest. What we will show is that the order is always, it will always be a divisor of G. So we will show that for all x in G, order of x always divides the size of G. How will you prove this? Okay. Yeah, let's call this N. This we call D. So the issue is in the orange part of the proof we had deduced that x to the g is E, right? And from this, what you are saying, you get that order of x has to divide g, has to divide n. But since we have condemned that line of argument, what will you do? Now we don't know why is x to the g equal to E, or whether it's even true for all x. So question here is, so you have to show that x to the n is E. If you can show that, then what you are saying can be done. And x to the d is E, then what you can do is you can define basically the proof we have done before, divide n by d, so you get n kd plus r with r less than d. Yeah, so you will then get that kd times x to the r is equal to E. What is x to the kd? Yeah, here you can actually do the following. You can actually write this as x to the dk I mean this is actually equal to x to the d outside k times x to the r. Why is that? Can you do this interchange in a non-abelian group? Yeah, you can do this because actually there is no other element other than x that we are talking about. If you multiply x kd times, you can as well decide that I will multiply x in blocks of d, k many times. Right? That doesn't contradict, that doesn't require any special axiom, that's just associativity. And which then happens to be E times x to the r, so x to the r, right? Which implies that r is 0. Okay, so when you divide n by d, the remainder is implied to be 0 because d was the smallest number, the order, which always exists. Okay, so that's the proof that d divides n. Is this clear? So if you are willing to accept a false proof here in the orange part, then we are done. Is there any problem with that proposal? Some of you will object, but then I cannot finish the proof now. We'll finish it next week, okay, because that will require a big concept in group theory, which is cosets. Okay, so we'll define cosets and then we will come back and we will prove that x to the g is E. Right now we don't have the tools to finish this proof. Any questions? Okay, so yeah, so you can just recall the proofs of Fermat's little theorem. in this new light. Okay, so the things we did to prove the Fermat's little theorem and Euler's theorem was basically these more general things, and the group there was Zn star. Okay, so Zn star is an abelian group, finite abelian group, and the claim and the theorem together give you all the properties in the number theoretic example. Okay, then it's a complete proof, but for abstract groups, you have to work harder. You have to define new objects, which we will do in due course. Okay. Right, so this tells me that the following definition may be useful. So we can call G, group G cyclic if essentially the thing that you did with fields, the finite field, we defined a primitive element, right? So we call a group a cyclic group if there is an element X which generates everything. So if there exists an X in G such that the group generated by X alone, which is this X to the J's, that covers every element in the group. Okay, then we call the group to be a cyclic group. And X is called a generator. In the same spirit, we can also take a subset of group elements and we can define this notation where S is not a singleton anymore. It may have 2 elements or 3 elements or infinitely many elements. And the notion of generating a group is that you do all possible multiplications with elements of S. So basically you are allowed to do this for all subsets contained in S. Well, I also want repetition, so why not say T is a multiset of S. So essentially what you are doing is you can take any number of elements from the set S and you can also repeat them. Yeah, this still doesn't capture. So multiset has to be ordered. So let's just write that what I want. So T is an ordered subset of S with repetition. Okay, so you basically pick as many elements as you want from S and with as much repetition as you want. And you are taking it in order, and then in that order you do the multiplication and you get an element in G. Okay, so you collect all such elements of the group G. What you can immediately see is that this again is a group. This set is a group because you can multiply two such things and they are of the same form. So this is again a group. It obviously has identity element E, inverses, etc. Everything is there. So this is called the group generated by subset. Okay. I don't think we'll use this, but this is where the notation of this parenthesis x comes from. You can do this with many x's, not just single x. It gives you, basically you can think of it as trying to do recursion. These are substructures inside the group. The group may contain smaller groups. So these are the ways to get all of them.